Good evening and welcome to the Science in the News Fall Lecture Series. This is our fourth lecture of our 9-part series, and this lecture is titled Our Universe's Story, Cosmos from Chaos. We're going to be getting started in just a couple of minutes, but remember that during the lecture you can use the form below to ask questions and also provide feedback on the lecture, your enjoyment, and your viewing experience. Again, we'll be getting started in just a few minutes, and thank you for joining us. Hi everyone, good evening. Welcome to the Science in the News lecture series. My name is Kelsey.
My name is Vinny.
We're the co-directors of Science in the News. Science in the News is a graduate student organization here at Harvard University. It encompasses all the Graduate School of Arts and Sciences. And our goal is to bring scientists and non-scientists together in fun, informal, educational environments through our events that we provide. So our main event that we do, of course, you're here for, is our fall lecture series. We've been having this lecture series for 15 years now. And if you didn't get one of these already, I would encourage you to grab one during intermission or on your way out because it has our full schedule on the back. Right now, we are on our fourth lecture of our 9-part series, which is every Wednesday here at 7 p.m. In addition to our fall lecture series, we also have a spring lecture series. That one occurs on the Cambridge campus. at Harvard University, and so you can keep a lookout for that in the spring. We also have a fun event called Science by the Pint. This is a really casual event that occurs at the Burren in Davis Square the second Monday of every month. Unfortunately, we ran out of flyers for that event, but our schedule is on our website, and we should have more flyers next week. And lastly, we have an online blog called Signal to Noise, in which we post articles about various science topics that are currently hot in the news. And so I'd encourage you to check those out on our website. So Vinny's going to tell you about how tonight will work.
All right, so it's good to see some frequent flyers in the audience. Hello to everyone. So most of you know how this works, but for those of you who are here for the first time, our lectures are generally split into 3 parts. And each part is about 20 to 30 minutes, and each speaker will pause for questions a couple of times where they feel necessary. So maybe hold your questions until the end, until those question breaks. And we also, if you notice, our speakers will also be repeating the question that you asked them. And this is because we have some viewers on the live stream. Hello. And they will also be able to ask and hopefully get their questions answered by this team over here. So today we have Stefan, Kate, and Zach, who are going to be presenting to you the universe's story from cosmos to chaos. At the end of the lecture, we will also be having some demos right up here at the front that these 3 awesome graduate students will be leading. The other thing, we also have surveys, and these, if you could fill these out, this would be awesome, because this helps us tell us what we're doing right, what we could do better, and also any topics that you would like to see in the future. We actually really take these seriously. So without further ado, I'll turn it over to Stefan.
All right. All right, good evening, everyone. I'm Stefan Portillo, and I'll be presenting tonight with 2 of my colleagues, Zachary Slepian and Kate Alexander. We're all third-year PhD students over at Harvard University's Department of Astronomy, which is one half of the larger Harvard-Smithsonian Center for Astrophysics. And tonight's topic is cosmology, the study of the universe, or as we've titled it, our universe's story. And kind of the theme of tonight is going to be talking about how the universe started in a chaotic state, started as a chaos, and turned into a cosmos. Now, cosmos is a Greek word meaning order or beauty, but Pythagoras was actually the first to use it to describe the order of the universe. But where did he get this idea to apply the word cosmos to the whole universe? Well, it all starts by looking up at the night sky. Almost every ancient culture has some form of astronomy. The first thing you notice is the night sky is full of stars, if you can get away from the light pollution of cities. And you can notice these stars' movements and keep track of them. One big feature you'll notice is this band that goes from the center of the image and goes up and to the left. The Greeks called this band of light the Milky Way, and they imagined it as a giant circle that surrounds the observer at all angles. Other cultures also named it the Milky Circle or something to do with milk. Other cultures called this the Great Heavenly River. But, you know, it's a pretty obvious feature to notice, this big circle on the sky. But ancient astronomers also noticed that some stars moved very differently from all the other stars. They moved along a fixed path. And this fixed path is the same path that the sun and moon follow. This path comprises another circle that the Greeks called the zodiac, or the ecliptic. And ancient astronomers, especially the Greeks, noticed all sorts of patterns in the night sky. And to them, it seemed like a very ordered and balanced system, a cosmos. And although they gained these insights just with their eyes, there are other questions they wanted to answer that they didn't really have the tools to do. Here we see how the cosmos looks in the present day, but what was it like before? How did it get to be the way it is now? And what will it be in the future? Unfortunately for the ancient Greeks, those were questions they couldn't answer scientifically. They then turned to their philosophy and religion to answer these questions. But as we get into more modern times, we'll see that basically technological advancements have allowed us to gain a better picture of how the cosmos came about. So the next part of my story will be in the 1600s with the Copernican Revolution. The debate over the nature of the zodiac, the nature of the solar system, and whether Earth or the sun was at the center of the solar system. Here I've got a picture of the Danish astronomer Tycho Brahe, and he is famous for his Uraniborg observatory. And his observatory is famous because Brahe was a stickler for precision. He wanted to be the astronomer that made the most precise measurements of the stars possible. And he succeeded because machinery had just come into full bloom at this time, and he was able to ask machinists to make giant wall murals for him and really precise clocks and all sorts of other equipment that you need to make measurements of the stars. And because of the combination of this equipment and Brahe's determination to be the most precise astronomer out there, Kepler was then able to use Brahe's data after Brahe's death to prove that the sun had to be at the center of the solar system. This is only possible at this time because of Brahe's instruments. If we go forward another 2 centuries, it was only with the invention of the telescope that we were able to really figure out what the Milky Way is. If you point a telescope at the Milky Way, you'll see that the Milky Way is just a bunch of stars really close together. This left-hand diagram here is a map made by William Herschel of the position of all the stars he saw in the Milky Way. He realized that the Milky Way was actually a disk, and that we live somewhere inside the disk. And that's why we see it as a circle on the sky. But astronomers were also looking at other objects with their telescope, and they called these objects nebulae. Today, we know that most of them are clouds of gas and dust, but back then they just looked like blobs on the sky. But some of these blobs looked really fancy, actually. They had these nice spiral patterns that all of the other nebulae didn't have. And why would there be spirals in space? What's going on? It took yet another century to get at the nature of these spiral nebulae. At about 1920, Harlow Shapley was an astronomer that was, at the time, applying to be the director of the Harvard College Observatory. He thought that the spiral nebulae were pretty much like all of the other nebulae. They just happened to have a spiral shape. But Heber Curtis was an astronomer who thought that the spiral nebulae were special, that actually these nebulae are galaxies, disks of stars just like the Milky Way. And if we could see the Milky Way from outside, they would look like these nice spirals. But this debate couldn't reach a conclusion until the 1920s with the Hooker telescope at Mount Wilson Observatory and the observer Edwin Hubble. He was able to measure the distance to one of the spiral nebulae called the Andromeda Nebula. And he said, the Andromeda Nebula is actually the Andromeda Galaxy. It's so far away from us that there's no way it could be part of the Milky Way galaxy. It had to be a galaxy in its own right. And Shapley actually still got the job at Harvard College Observatory, even though he was wrong, but that's another story. So I've come up to the 1920s here, and in the past 100 or so years, there's actually been an explosion in knowledge about our universe. And you've probably heard of the Big Bang Theory, not the television show, but the theory of cosmology. And the main story we want to tell you tonight about the Big Bang Theory is that the universe started with a Big Bang. And this is a state when the universe was very hot and dense and nearly formless. The universe had just exploded into existence. Every place in the universe looked like almost every other place. Every direction you'd look, would look like every other direction. It's just a giant explosion. There's not much going on, a very chaotic state of being. But if we look at the universe today, we see galaxies. And not only that, we see that the galaxies are arranged in a cosmic web of structure. And not only that, the universe is much colder and sparser than it was before. And this is the ordered cosmos that we see today. And tonight, we want to tell you how the universe came from chaos to cosmos. And we'll actually be going back in time to step you through this. For the rest of my talk, I'll be talking about the state of the cosmos today and telling you what we need to understand about how the universe is today in order to understand where it came from. Right after me, Zach will pick up where I left off and tell you about the growth of structure. And what I mean by that is the Big Bang was nearly formless, but there are actually these little variations that we call perturbations, little tiny areas that were slightly hotter or colder. And it turns out that these perturbations actually grow into the structures we see today. And Zach will step you through that process by way of explaining galaxy clustering. He'll tell you how that cosmic web of galaxies comes about. After the break, Kate will finish up our talk by explaining the theory of inflation and current efforts to prove or disprove this theory. And inflation, as these tiny perturbations I talked about, had to come from somewhere. And inflation is our current best theory for how these small perturbations came about that you need to grow into galaxies today. So with that in mind, I'll start on the rest of my talk and tell you about the state of the cosmos. And there's basically three key facts, three key statements that I want to get across. The first being that the universe is currently expanding. And for this knowledge, we have to thank Mr. Hubble again. When he discovered that the Andromeda Nebula was actually the Andromeda Galaxy, he decided, hey, I want to find all of the galaxies that I possibly can and measure things about them. When he did so, he found a surprising relationship. The galaxies that are farther away from us are, well, first of all galaxies seem to be moving away from us. That seems strange. More than that, the galaxies that are farther away from us are moving faster away from us. So why is everything moving away from the Milky Way, and why are more distant objects moving faster? This all makes more sense if you think of the universe as a balloon, which is an analogy astronomers love to use. So we live in 3D space, but imagine that we all live on the surface of a balloon. The surface of the balloon is our entire universe. Here I've represented this by taping galaxies onto the surface of a balloon. If you inflate the balloon, the space between the galaxies appears to get bigger. And if you imagine that we live, say, on this red galaxy here, it looks like all of the other galaxies are moving away from us. But that's just because the balloon is expanding. This also explains Hubble's relationship, because this galaxy over here that's farther away from us will appear to be moving faster because the space between us and that galaxy is greater and it's expanding faster. The fact the universe is expanding is important because today we observe that the universe is very cold and sparse. But if it's expanding now, it must have been smaller in the past. And if you put all of the radiation and matter in our current universe and put it into a smaller space, it will get very hot and dense. And that's the key point that I want you to take away from the fact the universe is expanding. It tells us that the universe had to be smaller, hotter, and denser in the past. The second statement I want to introduce is that galaxies are arranged in structures. This is the cosmic web that I was talking about earlier. Here at the Harvard-Smithsonian Center for Astrophysics, the CFA Redshift survey was conducted. What the survey was is basically a map of all the galaxies astronomers could find. Imagine that Earth is at the center here, and we're looking outwards in distance, and this is a slice of the sky. every dot on this diagram is a galaxy. And one thing you notice is that there seem to be structures in how the galaxies are arranged. There seem to be, things that look like walls. This kind of looks like a stick man here. There's spaces in between where there's no galaxies at all. And this isn't what you expect if galaxies are just randomly or evenly distributed. Instead, there seems to be something dictating how the galaxies are arranged. And this was a big surprise when Valérie Lapparent, Margaret Geller, and John Hucra looked at this data in the 80s. So move on further. I'll pause here to take any questions from the audience. Up there. So for the live stream, the question was the Big Bang actually a bang? And you're correct. You shouldn't technically think of it as an explosion. It's just that the universe was a lot hotter and denser than it is today, so it would feel fiery almost. But we're actually the first moments of the universe. Kate will tell us about inflation, a theory for those first moments. But I guess kind of a better way to think of the Big Bang is it's really when space and time themselves came into existence. It doesn't make sense to talk about before the Big Bang because time came into being with the Big Bang. It's a hard point in time to think about. Astronomers will romanticize it as like an explosion, but really wasn't. Yep. So there is. I won't go over the details here. You can ask me during the break. But using something called redshift, which I can explain during the break, we can actually measure exactly how fast the galaxies are moving away from us. And sorry, for the live stream question is, can you measure the velocity of galaxies away from us? Right. So the question was, if farther away galaxies are moving even faster away from us, won't that eventually break the speed of light limit? And the cool thing is actually you're allowed to break the speed of light in this way because the galaxies themselves aren't actually moving. The space in between galaxies is expanding and makes it look like the galaxies are moving. But there actually isn't physical motion in the normal sense. So you're allowed to break the speed of light because it's not like physical motion. So like if you think of the galaxies on the balloon, those galaxies like if you imagine living on the surface of the balloon, those galaxies are staying still. The rubber is just expanding. I'll take one last question here. Right. So as far as I know, so the question was, all the galaxies, Hubble found all the galaxies were moving away from us. Wouldn't that have created some notions that we were the center of the universe, just like before the sun was discovered to be the center of the solar system? And as far as I know, that didn't come up because by this time Einstein had made his theory of general relativity, which is where this balloon analogy comes from, the idea of space expanding. So it was pretty clear that that was the correct answer by that time. So I'll be happy to take more questions at the end of my talk or during the break. But for the rest of my time, I'd like to go over my last statement here. I've told you that galaxies are arranged in structure. Now, I'm going to spend the rest of my talk on this important substance called dark matter, and the fact that dark matter actually makes up most of the structure in the universe. So what exactly is dark matter? I'd like to know, I don't know. I can tell you what it's not. It's not baryonic matter. Now, what's baryonic matter? It's some fancy name that particle physicists have come up with. By baryonic matter, we really mean all the matter that you encounter in your everyday life, here in this room, and even most of the stuff you think of in space, like the sun or other stars or nebulae or black holes. All of those are baryonic matter. Almost everything you can think of is baryonic matter. Baryonic is a fancy word, so I'm going to try to call it visible matter or regular matter for the rest of the talk. The reason I call it visible matter is that the defining property of baryonic matter is that it interacts with light. One example of an interaction with light are the light bulbs in this room and the light bulb in the projector. They have energy being put into them from the electricity this building is getting. And because of this electricity, the light bulbs in this room are emitting light that we can see. But I mean, the universe isn't made out of light bulbs. What about everything else that isn't a light bulb, like me? How do I interact with light? I'm made of baryonic. But how do I interact with light? Well, the fact you can see me indicates that I interact with light. The light from the light bulbs is striking me, striking my shirt. My shirt absorbs all of the light except the green light. It reflects the green light back at your eyes, so you can see I have a green shirt. That's how I interact with light. But there's an even deeper interaction with light that all baryonic matter has. I'm not a light bulb, so you might say I'm not glowing in light right now. I'm not giving off light on my own energy. But I have a temperature. I'm at, I forget what body temperature is. I'm not a medical scientist, but because of the heating in this building and the heating and the earth being heated by the sun, everything has a temperature, which means that it actually does emit light. For most everyday temperatures, things emit infrared light. I emit infrared light, the table emits infrared light. Everything emits infrared light because it's at room temperature. And you can see that if you have an infrared camera. So that's because the energy I absorb from the sun and the heat, I re-emit as infrared light. So really, everything you can think of interacts with light in some way. And that's because almost everything you can think of is made of protons, neutrons, and the components of the atom. And the protons and electrons love interacting with light. The reason I make a big deal about visible matter is astronomers study the universe by looking at light. We can see stars because they produce energy from nuclear fusion. They produce energy on their own, so they glow, just like light bulbs, except way brighter. But all of the other stuff in space, like the gas and dust that doesn't generate energy, we can still see because it absorbs the starlight. It's heated by the starlight, reflects some of it, and also glows in the infrared. So using light, we can actually see all of the baryonic matter, all of the visible matter in the universe. And astronomy has advanced so far that based on the amount of light that we see from stars and gas and dust, we can tell exactly how much those stars and gas and dust weigh. So dark matter became a concept when we started being able to weigh objects in the universe using methods other than looking at their light. So the next story I want to tell you, starts with a pizza. So I have a chef here throwing a pizza around, and when you rotate a pizza, you're exerting centrifugal force on its edge that makes the edge want to come outwards, and that's why the pizza dough expands. But the pizza dough doesn't expand indefinitely. It doesn't splatter all across the room, at least if the chef is skilled enough. So why doesn't the pizza dough expand indefinitely? What force could be keeping it together? Does anyone have a guess? So I heard centripetal force, which is correct. You need a force. So centripetal force just means a force pulling inwards. But what could be creating that force? What's the fundamental cause of the centrifugal force? Stretchiness. I called it stickiness. Well, actually, I called it tension, but the same idea. We know that dough is sticky. It stretches, and that's because all of the molecules in the dough are interacting and don't want to let each other get too far away. So the tension in the dough keeps the dough together as a unit. So what does a pizza have to do with dark matter? Replace the pizza with a galaxy. So a galaxy isn't made of pizza dough, so it's not tension that keeps the galaxy together. Does anyone have any guesses as to what keeps the galaxy together? That's exactly right. So gravity keeps it together. And gravity comes from having mass. And the idea is the galaxy has to have enough mass to generate enough gravity to overcome the centrifugal force and keep itself together. So if we can measure the rotational speed of the galaxy, we can calculate how much mass the galaxy needs to have to keep itself together. The thing is, Vera Rubin tried to do this in the 1980s, and she got a different answer than what you get for the mass of the galaxy if you count all of its stars and weigh all of its gas and dust. In this graph up here, you can see that the gas makes up something like 1 to 4% of the total mass of the galaxy. The mass of the galaxy, to keep itself together, is much greater than the mass that you see in gas. And when she started to add stars to the mix, it turns out that visible matter, the stuff that stars and us are made of, only makes up 20% of the mass that you need to keep the galaxy together. So Rubin's observations were the first convincing argument for dark matter, but it's actually been supported by many lines of observation. I'll go over one more modern one that comes to us thanks to, again, Einstein's theory of relativity. So according to general relativity, if you have a lot of mass in one place, it can actually bend the very fabric of space and time. And clusters of galaxies are really massive objects, and they can actually bend space and time so much that we'll notice. The way we notice is if we're over here, there's a galaxy cluster here, and some lonely galaxy way farther away, the light coming from this distant galaxy gets bent because space-time is bent here. And that means we'll see the image of that faraway galaxy as looking really weird. One way to imagine this is through this picture of the bottom of a wine glass on top of a sheet of graph paper. You know that the graph paper has to have straight lines, but in the image, the lines closest to the center of the glass look really bent. And here is what it looks like when we look at a galaxy cluster. All of the orange galaxies belong to the cluster, and this blue galaxy here is way behind the cluster. And you can see it has a really funny shape. It's in an arc. There's no way a galaxy is shaped like that. We know that it has to be bent. And from the amount of bending we see, we can calculate how much mass that cluster has to have. And again, it turns out there's more mass in the bending. You need more mass than you can see with the starlight of all these galaxies. There has to be dark matter that doesn't interact with light to explain this bending. So all we really know about dark matter is that it's there. It keeps the galaxy together, and we see it in galaxy clusters because it bends light. And because we don't see it otherwise, we know it can't interact with light in any way. It doesn't emit light. It doesn't absorb, reflect, or re-emit light, so it isn't like everything else. So that means it can't be made of the same stuff that atoms are. And it gets worse than that. You might have heard of the Large Hadron Collider over at Geneva. It and its particle collider predecessors have been discovering new particles left, right, and center, not least to say the Higgs boson. But none of these new particles can be the dark matter. They don't have the right behavior. They all interact with light, unlike the dark matter. So it's really a mystery as to what the dark matter is. But fortunately, Sherlock Holmes and my advisor are on the case. So this is Douglas Finkbeiner, my advisor here at Harvard. And his group is currently using data from the Fermi Space Telescope, a telescope that sees the gamma ray wavelengths of light. And you hope that, basically, if you're looking for dark matter, one good place to look is the center of our galaxy, because it turns out most of the dark matter in our galaxy is the densest there. Earlier this year, we actually saw that there is this funny signal at the center of our galaxy that doesn't fit any of the explanations we've come up with so far. And it's consistent with what you would expect from dark matter. It's centered at the center. It satisfies the list of things you would want from a dark matter signal. But the problem is, to say that this is dark matter, you have to rule out all other possible explanations. And currently, there's no way to do that yet. So the jury is definitely still out. But the point is, there are groups around the world that are trying to find out what the dark matter is. So we've got people on the case. So I've told you that the dark matter, even though we don't know what it is the dominant form of matter in the universe. The visible matter is only 20%. So should we care about the visible matter at all? Is it going to be important in our later story? In some sense, no, because the dark matter is the dominant matter. It has most of the gravity, so it will pull the visible matter around, and the visible matter doesn't have much choice. But on the other hand, everything we care about is made of visible matter. Galaxies only form because visible matter likes forming galaxies. Stars only form because of the things that atoms do, and so on and so forth. Everything we care about is visible matter, so we need to understand it. So I told you earlier that the universe is expanding, which means that it used to be smaller and hotter and denser. And that fact is important because when you make visible matter hotter and denser, it interacts much more with light than it normally does. Right now, I'm interacting with light just by reflecting it. But if you make matter hot enough, it can actually get pulled around by light, which is not something you normally encounter. And in the next part of the talk, Zach will be telling you more about how matter interacts with light when it's hot. So just to wrap up my section here, I wanted to tell you about the state of the cosmos. And I had 3 statements to convey. First, the universe is currently expanding. Second, galaxies are arranged in a large-scale structure, a cosmic web of galaxies. And we want to know where that comes from. And finally, galaxies, galaxy clusters, this whole entire structure is actually almost entirely composed of this substance, dark matter, whose identity we don't really know, but we know it has to be there and that it doesn't interact with light. And the final note I'll have here is a theme that I hope you'll see throughout the talk, is that the preciseness of our cosmology, the fact that we were able to come up with the Big Bang theory and tell you the story, is only possible because of technological advancements that have given us better and better telescopes that allow us to take more and more precise data that allow us to test all of the theories that we're telling you about here. So with that, I'd like to take any questions from the audience. Thank you. Oh, sorry about that. So I think, so the question was what Einstein's problem with the beginning of the universe was. So you might be referring to Einstein's comments to Georges Lemaitre, so Georges Lemaitre was actually a Catholic priest who happened to be an astronomer on the side. He came up with the Big Bang theory. Einstein wrote to him, "Your math is correct, but your physics is wrong." You might be referring to something like that. So I can explain this in more detail in the break, but let's see. So Einstein's relativity and Hubble's observations that all of the galaxies are moving away from us were all being developed at around the same time. And when Einstein came up with relativity, the thought at the time was actually that the universe wasn't expanding. Hubble hadn't made his observations yet. So Einstein drew up this nice theory and made it so that the universe wasn't expanding. And it wasn't until Hubble's observations were accepted that the Big Bang theory was believed. So I think that comment is actually from before Hubble's observations became widely known. So the question was, is there a consensus on what the universe will do in the future, whether it'll keep expanding or whether it'll contract in the future? And the smart money is always on, we don't know. But based on, if you extrapolate our current theory tells us that our universe is filled with dark energy. I'm not going to open that can of worms. I can explain that more in the break. But if you go by just the stuff we currently know, dark energy is this force that makes the universe expand even faster. So the extrapolation of our current theory would be that our universe is just going to keep on expanding. But we can always discover some other force that goes the other way. So really, it would be wise to say we don't know. Right, so I should clarify. So the question was, doesn't dark matter keep everything together? And I should have made a better point of, so astronomers like dark things, apparently. Dark matter is a different phenomenon than dark energy. The reason they're called dark is we don't know what they are. They're dark and mysterious, something like that. So dark energy is different than dark matter. So dark energy actually makes things expand. So the question was what I think of the theory that, from string theory, that brains, these objects in string theory, are connected through gravitons, the force of gravity. And right now, we're a far ways away from being able to test that concretely, but experiments like those at the Large Hadron Collider are actually looking for evidence of things like extra dimensions, which would be, so you do need, so string theory predicts things like extra dimensions, and people are currently looking for that at the LHC, but it's hard to, I'm not sure if I'm optimistic that we'll see any results from that in the next couple decades. I'll take 2 more questions here. Mm-hmm. Right. So the question is, I define dark matter as not interacting with light, but what if it interacts at some wavelength we haven't been able to observe yet? So there's, so I'll answer in 2 parts. The first is, we have observed a pretty large range of wavelengths, going all the way down from radio all the way up to gamma rays. That is a pretty large swath, and there are good reasons, like atomic physics and other things like this tell us that most of the stuff we care about happens in these frequencies. But still, there is a good point that, you know, we haven't looked at everywhere. It could be hiding somewhere else. There's actually, so later on, my colleagues will talk about something called the cosmic microwave background radiation. I'll let them tell you more about that. But from that radiation, we can actually show that the dark matter can't interact with light in any wavelength. It's pretty excluded. I can tell you more about that during the break. I'll take one last question here. So our galaxy is enclosed in what astronomers call a dark matter halo. You can almost kind of think of, I guess I like imagining that last scene in Men in Black where the galaxy is in a marble. Kind of like that, where the dark matter is the sphere of stuff that our galaxy sits in, and the sphere is densest at the center. And then you should also imagine, like, in that diagram I showed of the distribution of galaxies, each galaxy has this halo, and the halos are connected by filaments of dark matter. And Zach's talk will actually show you more of the detail of how dark matter moved around in the early universe. So he'll be able to show you some of that. So I'll take more questions during the break, but I think for right now, I'm going to hand it over to Zach. Oh, sorry. And
thank you. Give me a moment here. We have a double-barreled microphone system because we have a live stream as well. Right, okay. So first of all, can everyone hear me well? Back there up in the nosebleed seats? Great, okay. So as Stefan said, I'm Zach Sleppy, and I'm also a third-year graduate student in astronomy at Harvard. And I'm incredibly excited to be bringing this part of the story to you today. I think one thing to highlight before we kick off is actually that you are living at a special time in the universe's history, because you are living at a time when human beings have actually been able to understand a lot of it. And a couple different things have enabled that. First of all, space exploration, which started in the 1960s and continues to this day, let us put satellites above the Earth's atmosphere that are able to do these observations. Although a lot of the observations I'll be telling you about have actually been done with ground-based telescopes instead. There's a dependence on the type of light you want to look at as to which is best. Secondly, computers. Starting in the 1980s, computers have really enabled a revolution in the amount of data we can process and the amount of data we can record. And so everything, well, not everything, but a lot of things that Stefan said, especially the more recent results he showed with his own advisor, are actually cutting edge. And as he mentioned, are sort of very much unresolved questions that I think are the greatest questions of our time. Really, these are the greatest questions of our time. And it's my hope that in our generation, people like Stefan and me and Kate will contribute to resolving them, but who knows, it may take hundreds of years. And a lot of the measurements that I'll be talking to you about have also been done in the last 5 or 10 years. And so let's get into those measurements. So we look at an updated plot of the clustering of galaxies. You'll remember the stick man that Stefan showed you earlier. Well, this is the modern day version of that. This is from of the entire universe, well, as far as we can see, essentially, called Sloan Digital Sky Survey. And each point in this picture is actually a galaxy. So this galaxy here that I'm showing you in kind of orange doesn't necessarily look like a galaxy that you might be familiar with. It's kind of just a blob. This is what's known as a luminous red galaxy. And they're very massive, very bright galaxies, hence the name luminous. And they're red, reddish orange. And basically these are really good to look at because they're quite visible even if they're far away, just like a very bright headlight is very visible even if it's far away. So I mentioned that these observations were done with a ground-based telescope. This is the Sloan Digital Sky Survey telescope. It's a 2.5 meter, or approximately 7-foot telescope, although they don't use the entire width of that. We actually have a little surprise from that telescope for our demo later, and you'll get a more hands-on look at that. This is an Apache Point, New Mexico, so this is a US initiative, and it's been running basically pretty continuously for the last 15 years, taking these pictures. So just to go over what this plot is really showing you, this is distance from us. We're right at the center. This galaxy over here is as far away from us as the survey goes. And then this rotation around the circle is just talking about the angle on the sky that you're looking at. So you'll notice there are two big chunks missing. That's because of the Milky Way. You can't see through the Milky Way. It's too dusty and too dense. So now let's zoom in on a little region here. Just focus your attention on this blue circle in this picture. And on my next slide, I just want to really make that big. So you see that, as I've said, each of these dots, each of these yellow and orange dots is actually a galaxy. And it seems that there's a characteristic pattern of sort of voids where there are no galaxies, and that galaxies like to live on the edge of these voids, and that if you superimpose circles on these voids, those circles all actually have the same size. So I've gone ahead and done that with a few. So really, this is a three-dimensional measurement, and this map is just projecting that down onto a page so you can see it. So these circles are really just what happens if you slice a sphere. So this is really saying that there are spheres of galaxies, and those spheres all have a characteristic thickness or radius to them that I've just drawn in here. All these spheres are just the same distance apart. So what this is telling us is that galaxies actually like to be separated by a certain amount from each other, no more, no less. Now you can see there's some other structure along these sort of filaments where galaxies are closer to each other than that. That's unfortunately something I won't be able to address as much, but I'd be glad to chat about that later. Today we're going to be focusing on why galaxies are good neighbors, why they like to live far apart from each other. You know, just like in a neighborhood, you kind of want some lawn space between you and your neighbor in case he or she is loud or noisy or has a lot of dogs. Sorry, dog people. Galaxies seem to behave in the same way. And we're going to find out why. And I'll just, spoiler, it's not because they're worried about the noise of their neighbors. Okay, so another way to slice this picture we just saw is what we call the correlation function of galaxies. So this is a little bit scary. Let's step through it point by point. This horizontal axis is the distance from us. We'd be sitting at the number 0 here, which I actually cut off so we can focus on things that are a bit more distant. The distance units are very huge units. They're units we call megaparsecs. A megaparsec is about 3 million light years, or more familiar units, it's about 30 times the width of our galaxy. So this right here is 150 times 30 times the width of our galaxy, or like 4,500 times the width of our galaxy. So this is basically saying, okay, at a given distance from us, what's happening at that distance? And the y-axis, this vertical axis, is showing us what's happening. This vertical axis is actually plotting the extra galaxies you get at that distance over what you would expect to get if galaxies were distributed in space in a completely random way.